channel right now, and please reply to my comment there, saying reply here if you want to participate time series data. Those who want to do the supply chain, send me a message through Slack. We can think of something.
I created a thread, so just put it in the thread.
Yes. Last thing, last but not least, so we can get the project going on.
I was wondering what the expected chemical was. I assume something like
What time is it this Saturday?
So
10 to 12, but this Saturday is going to be between 3 and 5. Okay? Woo. Okay, last thing, so we can be on the same page. Finally, here at the meetup, we have the last link for a Google Docs. That's a spreadsheet. If you enter here, those who want to participate in the project, you can put here your name. Now, here are some the skills that are going to be needed, the groups that we are going to create. A leader for each group is going to be assigned, and we're going to allocate people. But the idea here is for you to put the fields that you are comfortable on being met, on participating. And based on that, we're going to build the groups. Okay? It's on the meetup group. So if you come here to the meetup group, the discussions, beneath the Slack group link, we're going to have a Google Doc. In 2 minutes to do that, and then it's 6:30 and we can start.
Did you notice I added product management? There was a lot of back and forth. Teachers are web scraping.
Okay. We're going to have some water, we'll finish this, and then we'll start the class. We're going to have, if you go to the comments, the last comment is a Colab link. Click here. You're going to have the Colab access again. Then you put file, save a copy in Drive, and then you're going to have your own copy that you can edit.
Is it simple that we used last time?
I changed 1 or 2 things. Yes, at the meetup group, at the discussions on this class discussions, beneath those links that I asked you to click, we're going to have this link.
Is there any way to organize the top one index here? Join
Okay, so this Colab, this is the same one as the one that we had before. Basically, what we're going to do here is to continue with, we're going to jump to the ARIMA model, and then, unfortunately, we only have Windows seats. So we're going to jump to ARIMA model, and then we're going to go to LSTM. Okay, we're going to jump the naive version, etc. By the way, who here trying to change the stock ticker? Who here played with this a little bit? Change the stock ticker? Nobody, come on guys.
Last class I did it, but
Yeah?
not before. Yes.
Now the goal here, the goal that we are, those Colab documents, they are documents for you to play with. So we set everything on APIs, so you can actually have real case scenarios. We're going to run again using Apple, and we're going to start actually with today's date. So I'm going to run everything until we reach the point that we were last class.
Yeah. No. You go to events. The first link. Scroll down. See more event details. See more
Quick finance
comments.
is not.
And this is where it's all at.
Yeah, everybody wants a finance project here. That's because that's where the money is,
Is this playing
not where the.
or will it be uploaded somewhere else, the video, after the class?
It'll be.
Okay, so
Okay, it's recording.
do you remember the naive approach? Who remembers the naive approach? If you were to predict the price of a given stock, you just use the last one. Let's say the price of, again, the question, the price of Petrobras, the Brazilian oil company. What would be the price of Petrobras? If you know that yesterday was 194 reais, that's a very valuable information. But of course, it doesn't perform well. Now, moving average. Moving average, we grab the last 10 days of stock prices, remembering that we are using the adjusted closing prices, not the closing prices, because otherwise we would have to adjust for splits, dividends, etc. So whenever you play with stock values, use the adjust close. Now you have nice graphs. Moving average for 20 years. This. All right. Okay. Now we got into the interesting part. 635. Okay, is everybody on the same page? Let me get my marker here. Stationary.
Last year.
Yeah.
This chart, let me go to market.
Yeah.
This library, one, it doesn't beyond.
Can you use these terms, like what is stationary?
Yes, so that's what we're going to start now. So, stationarity.
I'll make sure I'll check.
The idea is this.
Okay.
Now we are going to use one model called ARIMA. Of course, ARIMA, we're not going to get into ARIMA itself too much. We're not going to stay there because we want to use actually deep learning, LSTM. But it's important for us to understand what's happening regarding time series and what was the progress of the thought on how to deal with this kind of data. Now, this model, it requires that the series is stationary. What does this mean? This means that, in average, the series in a given time, in average, the expected value is going to be constant. It doesn't change with the time. So the variance as well is going to be constant. And the covariance between time only depends on the delta of the time and not the place in time. Yes?
In English?
In English. The covariance, so the first one is clear, right? The expected value of that series is going to be constant throughout time. Does anyone have doubt about that? And please don't feel shy of raising your hand. Okay.
Some examples.
So you're saying that we're expecting the value to stay constant as opposed to going up in time. So it's a kind of a transformation.
Yeah, but that's what he brings.
Yes, that's the expected value. Whenever you go, I don't know, to Vegas, the expected value of whenever you're gambling is going to be negative, correct? And probably, given that you are in a given I don't know, slot machine, is going to be constant. Every time that you play, what you expect to gain here to the result is constant. Although it might change. It might be positive, it might be negative. Yes.
If it is constant, what is there to predict?
The expected value. So you expect that it's going to be the same result, although it might not be. There's a variance. The variance is constant as well. And finally, the covariance of this is the tricky part. So x2 and x5 is going to be equal of the covariance x7 to 5 and x10. Yeah. So these guys here, the covariance between 2 points of the two series, the series is going to depend not on the time that it is now. Actually, it's going to depend on the delta between the two numbers. Yeah, everybody's looking.
Is there an example?
Or it may also help to think about like what if you wanted to take the stock trend, right? That was going up, and you wanted to level it off somehow to just look at the. So the purpose of an arrangement, right? Maybe it's the
Yes.
2 and 2
Let me put this graph here.
to forecast that a little bit.
Let me try to see this rolling mean, but the idea is this. If you are, you saw the price of this stock. Let's look this. That's the price of this stock, correct? No. This point here, this is going to be the last point here. But actually, as we have this trend, this value is going to be a little bit up because of the trend. You're going to input the trend. Remember, it's last day plus, it's going to be, it's not the last day, it's last day plus the trend. This will be a good forecasting. But actually, what we're trying to do here, and that's the beauty about this stationarity, is that in every single point, you are trying to set the distribution of that variable to be the same. It's not going to change. So the value here at this point, let's pretend that it is a normal between a given number and another number. Let's say 20 and 10. Okay? This point here, if we don't put this variable as stationary, if we were only had trend, this would be a little bit bigger, and this would be between, I don't know, let's say that it's 1 up, 21 and 11. Now, what we're trying to do, that's a very, it's like this, but what we're trying to do is, for every single point, this distribution is going to be in the same level. The factor that generates that variable is going to be the same in every single point.
Would that, are you implying this trend will be a linear relationship?
Sorry?
If every the difference between 2 points are identical, that means it's linear, right? You can't predict the up and down.
Yes. Would you like to say
Do you mind if I take a stab at it?
Oh, of course. This is not a class. So, by the way, I sent this to the first class.
And
Let's share the.
yeah, with that, you can correct. I'm going to oversimplify it a little bit.
Yes.
But one of the points of an arena is to understand a bit about.
Would you like to write this?
Yeah, I'd like to do a drawing. Right, if you're saying that the expected value is a constant, right? If you think about like the equations of graphs that you played with in math classes, where math was not complicated and it wasn't quite as involved, right? If I'm just a constant, it's a flat value. So if I say y is 4, it just stays steady, right?
Right.
So this is not a horizontal line. It has an overall trend going upward, right? So what ARIMA does is I'm super simplifying it, so this is completely distasteful to people that know the full definition. That's fine, but if you look at this, there's a general trend going up, right? There's like a y equals 4x or something. It's tilted. So one of the things that Arima can help you to do is to stationize it, ordered mixed stationarized, which is to flatten it out and adjust some of these peaks and valleys so they can form to a flat shape. So the good thing about that is you can look for individual regions that are unusual, might have more activity than other regions in the time. And so if you look later on in the presentation, you'll see graphs that look more flattened out. And basically what's happening under the hood is it's trying to straighten the data into a flat setting as opposed to a tilted one. So you can see if there are irregularities. Does that makes better sense?
Yes.
ARIMN. And
That was perfect. It's not only, yes, it has a question.
Oh, so,
I'm sorry, what's your name?
Oh, I'm Steve. Hi.
Steve.
Hi. So I was wondering, so like, is it just like are you just transforming it, or like, what are the peaks and values in that?
No. So yeah, so that's why it's not only about doing that, and it's about doing a transformation that you're going to have, as you can see in this graph. It's going to be tilted like this, but you still have these peaks and values. But actually, the peaks and values, it's because the variable, it can take a bunch of different values. In average, it's going to be constant. The variance is going to be constant. But the actual realization of the value is going to capture this movement.
Does it help with prediction?
Yes.
Yeah.
So why does it help with the prediction? And that's the whole point of trying to do something like this. And that's why the beauty of this and the idea behind this is that what you are trying to predict, and always when we are doing data science, we are trying to predict the patterns behind the data. In this case, what we do whenever we're stationary, the series becomes stationary, is that in every single point, the factor that generates that data is the same.
Is this graph t at error of t versus minus t minus 1?
Yes, so that's a question of how you can get the data to become stationary. I'm going to get there just 1 second.
Because there's an econometric interpretation of that as well.
It's not econometric. To make the data stationary, it's actually pretty simple.
No, I'm sorry. Go ahead.
So the idea is that in each single point, you're going to have what you're seeing here is a realization of a variable, which would be something that it varies. Of course, it's a variable. So whenever it's a realization, it assumes a given point here, a given value. Now, this value here, in this case, it's more frequent. This value here is less frequent. So you can imagine that values here are more frequent, values here are less frequent. Okay? So the beauty is, every single point here, it's the same generating process. And the generating process is what we're trying to capture. As it is the same and we have a lot of realization, we have, in the end, a good database for make predictions. I think that's it.
You kind of normalize it.
Yes. Yes.
Getting rid of the peaks and valleys.
Yes. You can say that we are trying to make it well behaved. I think this would be a good way to put it. Okay? So, let's see here. So, this, let me click here. Now, I wanted to do this, but actually the beautiful thing is we have something that we can use to test if the series is stationary or not. And it's just a function. It's called the ADF function. And I did that for you already here. But basically, let me see, how can I explain this? Who wants to enter into the details of hypothesis testing and how you find out if it is stationary or not? Basically, this value here is the p-value. Remember, if p-value is low, HO must go. That's a nice way to remember it. HO is your null hypothesis. In our case here of the ADF, each test has a null hypothesis that you have to memorize. So in this case, in the ADF test, the null hypothesis is that it's not stationary. So you want to reject that. You want that it is stationary. So you want p-value to be low. This is the ADF test for the adjusted close price. It's too high. By the way, low is 0.05. Put that as a rule of thumb.
What's the situation you're describing as the null hypothesis?
The null hypothesis is that it's not stationary.
What is
yes.
stationary?
Stationary is whenever...
Stationary around that big line?
Yes, stationary is when every single time the process that generates the data is the same. So it's when you kind of detrend and eliminate some stuff.
So you have the picture on top and you have the picture down below. Is that?
That's the raw
is this
picture.
The shaker, the thing that just got hidden below? Is that the jitter around the red line?
Yeah, so this is without doing, I'm testing if this series is stationary or not. And I find out that it is not stationary. That's the result here. And then I say, look, I'm going to do some transformation, just like a normalization at the series to see if I can make it stationary. One possible transformation is taking log. That's one possibility. Usually, when you take log of some series, of some data, you are reducing the variance of the data you're taking. And we do that. We have the graph here, the result. But actually, you still have a high p-value. So the log transformation didn't help much. And finally, we do the diff. Now, usually, you have three transformations that you make into a database to make it stationary. First, you take logs that, whenever you take a log of a series, you can explain in terms of percentage that series. If I do a lot of different transformations, I lose the meaning of the variable. I might have a variable that is stationary, but I cannot understand well what that variable means. If I just take logs, I can think of, if I divide by the logs, I can think of it as a percentage instead of a real number. If I do difference, and that's the case, I'm taking the stock price, my stock adjusted close price, and subtracting by the previous day. The first difference makes sense. It's just how much it grew or decreased, right? So this usually is the second thing that you, or the first thing, it depends on what you're trying to explain, that you are going to try. Let's see.
I have a question.
Yes.
How do you get the p-value?
Sorry?
How did you arrive at the p-value?
There's a test for that, the ADF test. And there's a theory behind that.
Okay, but
I'm not going to enter that, but
is it
basically...
significant enough to 0.9 is significant enough?
No. You have to reach, well, the goal here of the p-value is to reject or to not reject the null hypothesis. If the p is very low, you reject the null hypothesis. So it's just a boundary. And very low, usually you use 0.05%. You can use 10% as well, but this would be a little bit loose, or 1% you would be very strict. So this would depend on the case that you're trying to make. If you are in a situation where you cannot, I'm not going to enter this because I would have to enter into type 1 and type 2 errors.
Okay.
And that's not exactly the goal here. Maybe on the, where's that? On the fundamentals.
The p-value is basically the percentage that you're incorrectly rejecting null, right?
Yes. So for those who are the first time that you are here, we have classes on Wednesdays that deals with building the algorithm, the more technical and theoretical details of that. Usually this class is more to how to build a project using time series, using AI in some given field. And then we get into a final model where we are going to build a startup on top of that. But moving forward, that's a very good question. So, all right, so good news. If we take just the first difference, we reach into a very low p-value, which means that this series, the series that captures if the stock is growing or decreasing, is a stationary series. Now we can move forward to ARIMA, because the input of ARIMA is a stationary series. Questions? Someone understood something?
What's the range of a low p-value?
Less than 0.05. This one, by the way, e minus 29 is divided by 10 to 29. Okay. Let's see here. Now I put it together here, a function for you to run the ARIMA. Look. So basically here we construct the ARIMA model. Of course that we already have a package for that. And then if you go to statsmodels.tsa.arima model, you have the ARIMA. And here, I'm building the model, ARIMA. And I chose 2 legs and 2 error terms. And I'm doing the first diff. Do you have the rhythm?
Yeah, it should be right there. No, it's in front of you.
So the model that we are running here, is xt, going to be equal, let me copy here, so a x minus 1 plus a2 xt minus 2 plus 9 comes the error term, xt is not this minus, it's wrong there. There's a convention that you should do the R unit expense. Minus B1 ET minus 1 minus B2 ET minus 2. There's some confusion. Okay. So what I'm doing here, and that this is ARIMA model. ARIMA AR is autoregressive. Autoregressive means regressing in itself. In this case, I chose two legs to regress my variable. So I'm regressing my variable in the time t. I'm trying to explain it with t minus 1 and t minus 2. MA means moving average, but actually it's not the moving average that we did before. It's on the errors of the series. And also we are doing two legs. What we are estimating here are those coefficients here and here. So we are looking at Apple stock. We made stationary. Now we have a time series of Apple stock stationarized. So for each time I have this, I'm going to run this regression. And I'm going to find these coefficients. Whenever, so fairly simple. So if I do have these coefficients, actually I can start forecasting. I can start looking for the future. Yes, please.
When you showed the distribution to choose the points, was that of the residuals?
The normal distribution.
So like between when you were showing the differences and you were saying, go back to that. So each line is the variance, right? And each one has like an own distribution. Is that of the residuals that it's looking at, or how are you finding
It's the
those?
error t minus 1.
No,
So it's just the
that's
differences
series.
of observations. It's not the
That's the
residuals.
stationary series. It's because it's too close, but actually it's something continuous that does this. It's one point each one of those. There's not straight lines put it together.
I see.
Actually, they are a series like this.
Okay.
Yes, please.
So when I see a signal like that, one of the first things I'd do would be not only time analysis, but I'd go into a frequency analysis to look for any kind of pattern. Look at Apple stock, for example. I would perform a Fourier or a fast Fourier transform in real time, and I would look at stock changes over a period of time because it might be. I would look for some clues that would be a periodicity, to look for a period. And then I could see the amplitude of the signal, and I could see the period. Does that make sense? I don't know.
Definitely, definitely. Yeah. So
Spectral. Yeah. Spectral.
this in our first class, I let me ask again. Do you see something here? Let's say you're going to make a decision. You're trying to, in your eyes, is this just random stuff, or you see something, some patterns here? That was the first question.
We have seen
Yeah, I see a couple modes of patterns in the data, and then I see a lot of noise.
You see a lot of noise?
A lot of noise. The high frequency component then is the noise. I would filter the noise out by
Yes.
using a high pass filter, and then filter the high frequency for
There are some patterns here.
I see three nodes basically, three peaks in the.
You see three peaks.
Yeah.
You see some values here.
Right.
Three peaks. And then you see that actually there are some times
Right.
where you're going to have a high variance,
That's right.
and other times that you're going to have a very low variance as well. Those are patterns that you're trying to capture. Those are patterns that, if you build a good model, they would be grabbed. Now, how they would be grabbed? This is a good model for these elements.
So to kind of summarize where we came from here, right? So we had a trending upward jaggedy line that was difficult to read. We stationarized it, which brought it to level. Now we can see possibly some areas where there are peaks. Maybe they correspond to times of the year. It's hard to tell, but we can see them better now, right? And then from there, we're trying to find a way to predict what these bumps will look like, and that's where the Ewing model comes out.
So look at these patterns here, the variances. If we work this, imagine here we have points that are being connected by a line. So it does this. Sometimes does this, sometimes does this, sometimes does this. If we were to add some trend, we would have if we were to add the previous date, because we did only one difference and we reached here, we would have the previous series. What is represented here is the factor that generated the stock value price is the same one in each single point. What the stock price looks like is the price yesterday plus the factor that generated it. Yes.
Did we just take a difference or did we take a log difference?
No, I took the log, it didn't work, then I took the first difference, it worked. If it hadn't worked, I would take the log of the difference. And if it wouldn't have worked, I would take the difference of the difference. If you go further than that, basically, you are losing the power of your model of the results. You're going nowhere. Yes.
So basically, if I understand this correctly, the zero means your predicted and observed value are identical. Is that right?
In predicting, sorry?
The model predicted value basically matches observed value. So therefore, you have the zero line, right? So if it's not, and then you
Yes.
say the unbalanced. So in other words, it is residual, right?
Yes.
It's expected that.
It is the residual, but I'm not saying that the residual here, in this case, is going to be a normal it's going to be a normal distribution in the zero.
No, it's the difference between predicted and observed.
Okay, so that's stationary. So we did the ARIMA model. The ARIMA model is this one, and we found these coefficients here. And now we're going to make the prediction. Okay, so here we have the previous series, and we have what the ARIMA model predicted for, as the price. Ram is not here, unfortunately, but last time he mentioned, look, there are some models that actually grab this value. So this model here seems to more or less, it's there. There's something there. I wouldn't put my mind.
Yeah, so is it possible to go from this stationary, predicted stationary version back into the tilted reality version, right? So is it possible to transfer back?
As we did only one difference, this way we can do that. We can do that. That's the problem. Whenever you're trying, to do a lot of transformations to make it stationary, then it's very hard to. It's not hard to go back, but more than that, it's hard to understand what's happening with your final series.
Are the coefficients informative at all once the model's made?
Yes, because you're going to see who is most responsible for the prediction or not. Actually, but nobody asked me this. Probably someone will. But how did I came up with those two numbers, two lags and two lags here? You have a methodology to do that. I didn't want to enter here to the methodology because we would spend a lot of time instead of going to LSTM. But basically, you have the autocorrelation function. If you do it, it's called ACF, and it's a package. It's pretty simple. Just put the series there, and you're going to have in the end something that's going to be like this. You do this one, and you're going to have something like this. So if you have something like this, it means that you have the first one. I don't know why it always appears, but this is like 0. So like 1, 2, 3, 4, 5, 6, 7. So you would put 7 lags. Now, regarding MA, you would have something different. So I'm not going to enter here, but basically, instead of the autocorrelation function, you would use the partial autocorrelation function. And from the merge of both, you can grab these lags here. Okay? But in a nutshell, the idea here from our first class and this class is to have an understanding of how all those filters, everything that I call filter, uses this. Some sort of the combination, moving average. You're not going to escape from that.
Yeah, I agree with you. I think you start with a moving average, which is a form of integration, and then you'd see the signals that would start appearing And then as you run a series of autocorrelations, the signals would obviously come right out of the noise. And that's just from, I spent a lot of time looking at signals and going between time and frequency domain.
That's perfect, yes. Yes.
So to get the just to summarize, like to get the parameters for ARIMA, you would run both ACF to get the AR and then the PACF to get the MA.
Yes, but the ACF is pretty simple to use, but the partial autocorrelation function, usually it's going to be something like this. You're going to have one up, you're going to have one down, one up, one down, one up, one down, one up, one down. Let's say that you have something like this, those are times. You would, from here, you would see some seasonality if this pattern happens. So there are a bunch of patterns that you're going to find, and each pattern has one significance. And one way to put this, as it is a finite number of patterns, in the end you grab everything. See, it's not that difficult at all. It's boring. And if you start to think about the actually unitary root, which is actually the mathematical meaning of stationarity. Those numbers here, they have to be, if this number here is larger than 1, you can imagine that you do that for the first one, the second, the third. As you are multiplying by something larger than 1, you are exploding this. So usually that's why you need stationary series to input here, because those numbers has to be between 0 and 1. So the series is, and you have predictions. Yes?
Can any data be made flattened like this, or are there series which cannot be flattened at all?
If you have series that are going to be, you're going to input there and they are going to be flat already?
No, I'm saying, is there like, is any series of data can be stationarized like this? Or?
No, it can, definitely, but sometimes you have to do so many transformations to the data that basically it loses the meaning.
So at what point do you discard that? So
if you do the difference, the first difference, and then you do the difference of the difference, and then if you do the difference of the difference, at some point you're going to get that.
Okay.
But
so I mean, what is
if you do more than, if you do after the second difference, basically it's better for you not to use this series.
Okay. So
unless you have other series that are going to be combined trying to predict.
So it's like a more than 2 or 3, this operations means actually
2, more than 2.
Forget about it.
Diff and diff and diff.
So
diff,
are there other techniques for those kind of data other than this?
No, if you took the diff and diff, that's it. You're good.
Okay.
Yes. I was just going to say, I think one of the benefits of doing this, or the deep learning version, is the fact that it will pick up non-stationary data, non-stationary variances very well. I mean, but you don't do all this before you feed it in, right? You just give it the raw data for the normal transformations, and it picks it up. In fact, if you transform it to be like a Riemann model or whatever, it doesn't work very well. But if you leave it alone, let's say you have something that oscillates and the amplitude gets bigger over time. It's like a textbook example. So the only thing I'm aware of is you're taking derivatives, so you need to have a continuous function, right? So if you have a break,
okay. So I'm not going to run the model because it takes some time and we would lose some time. But basically, in the result, we use the mean squared error for the level of error of our model, and we have 2.8. Remember that beforehand, we were having 5 point something with MA. MA was 10 point something, and the previous day prediction was 5 point something. So this model is an improvement.
MA.
Now let's move to LSTM. Yes. If you were to do what? Which? we were to transform it again, then probably because it's mostly Adam, if we were to do the Fourier transform there, would we wraps up?
That's the question.
But I would like to draw this. Let me get this because I like this cell a lot. We're going to draw here. Now let's go to the LSTM part, which will become interesting. How? Let's see if I can. I will draw a different. Okay. Before that, we have time. Yes, we do have 7 minutes. Who understands deep learning here? If I draw this. Look, if I draw this, who look at this and say, okay, I'm good? Everyone. I mean, for that, everyone. Someone still have doubts on this? No? After 4 months. Drawing this. Now let me get the LSTM. LSTM is fun. It's more interesting. I have a drawing here that's going to make things easier. So just okay. So how does it work now? Long short-term memory. You have a class of deep learning algorithms called recurrent neural networks. What does this mean? This means that whenever you have an information entering here, you have an information, instead of those things that we were constructing before, that you have the first information, and then we have the second, then you have the third, we were computing the cost, and then we back propagate to update our weights. instead of doing that, now we have the first information coming, the second information coming. But when the second information coming, there are some gateways that the first information is refitted with the second information. Now the third information is refitted with the second, the fourth, and so on. So that's how we do remembering in deep learning. The most simple way to do that, forget about these three things here. So we would have something, an information entering here, the model. This is the model. And basically, whenever you will have a prediction, the information flows back and the new information enters, and both of the information enters here. And so on. This is the most simple way to do that. So that's the most naive recurring neural network. What would happen in this case? As we have this function, this usually will be a 10H or a sigmoid function that will make those numbers here well behaved between 0 and 1 or minus 1 and 1. This previous information will be forgotten quickly. So if you want to remember long-term patterns, maybe you have seasonalities that you want to grab or something like that. This simple model wouldn't work. Now, in our case here, we are trying to make a stock prediction. We have daily prices. As we've seen, it's, yes. So, oh, excuse me, sorry, what's your name? No. Joe. Thank you. Vinicius. So, Joe, you mentioned that you were looking at patterns. When I saw this for the first time, I said, look, we're talking about here, so this is Apple. So 2001, 2011, 12, 13, 14. I might be wrong here, but I would say that there's something happening here. It is a pattern. If I had more historical price, this pattern, it might be a pattern that actually confirms itself. I would say that maybe Apple nowadays is in a high price, in a yearly base, because that's yearly base. Yes.
So you try to synchronize what events, you see what parents you get with a time event, with an event at Apple. You know, did they drop the price? Did they fall short on their sales or their product?
Cash App's good to do that, but why does it happen always? Like, I cannot say always because we have only 2 peaks here, there's a third one now. But let's suppose that this happens frequently. This would be a pattern. For some reason, you have some incentives to produce a lot today and sell a lot, and all of a sudden you have to restructure a little bit your company, and this happens. Now, if, as we are dealing with daily prices, and this is a yearly based, this here, only this part, wouldn't capture these long-term patterns. It would forget immediately. This capture, I don't know, 4 days. Now, LSTMs are usually used in a scenario where you want to do speech recognition, building, writing books. We can do that as well. We almost built a notebook on that today, but we didn't have time. And we have actually, Joe, you presented this natural language, right? So Joe made a presentation on creating a text using LSTM. Which author did you use?
Sherlock Holmes.
Sherlock Holmes. So he grabbed a bunch of Sherlock Holmes texts, and you predict character or word?
Character.
So you see, that's beautiful because he used not words, but characters. Each character he put in a sequence, and he put an LSTM model, and he tried to predict next, and next, and next. And all of a sudden, it starts to grab patterns. Now those patterns are grabbed here. So this first one is called ignoring, this one is forgetting, this one is selection. How does that work? Let's use the characters example. Let's put words, that is going to be easier to find some patterns. So let's grab two sentences. Joe ate apple. Let's use this, an apple, but let's use apple. Now, whenever we put here, let's say that we have a bunch of sentences like this, exactly like this. Just a variation of names and a verb in the name, in the middle. Now, whenever you put a word entry here, this guy here, this is a deep learning. This also is the same, is a similar framework. A bunch of weights that you can update through backpropagation and so on. So whenever you put the first word here, Joe, after these have been trained in a lot of sentences like this, this will understand what you will have to ignore. Basically, you're going to put the whole sentence. It's going to be, you want to predict Joe. So you're going to ignore things that are further. You're going to have an algorithm that is going to forget information. And you're going to have an algorithm that is going to select the word that you're going to use. Remember that you are feeding back the previous word. So let's say that the previous word was let's say the previous example was Donna had a cookie. So the previous word was cookie. That's the previous word entry, and you will input the whole database, your whole corpus here. As the last word was cookie, after trained, this model will understand that you will have to ignore the words that are behind the noun. This gate forgetting will be able to shift things as well. And this selection is going to select the name that is going to enter. That's the prediction. Remember, I'm inputting the corpus here. Cache it.
Yeah, so one possible way to think about this, adding on to what Manisha said, almost think about it like a waterway system. Like each of the gates, it's like the data is in the flow of the water, and the forget gate, like, you know, you're draining the water, the select gate, you're like, it's like all rerouting the water in a particular sense. So that's the analogy that I generally make when I talk about these. But these gates, you can like physically imagine them as actual gates, which the flow of the data and the processing of the data, how that's being, you know, what data is stored, what data is lost, etc. So it's just another way to think about it. It's a bit confusing.
As we have, the LSTMs are good because we do have some complexities here that it's not only about the words that he's trying to predict, it's about how the words are set here. So this whole kind of algorithm understands that words after, it would classify this as 1, 2, and 3. It would cluster these words like this. It doesn't know that this is a proper name, this is a verb, and this is a noun. It doesn't know this, but it would cluster like this. Why? Because he would use this ignoring and forgetting the selection tool. This is the idea behind LSTM. Now, it will grab not only, it not only makes the prediction of tomorrow, which we could use only the recurrent neural network, but it tries to grab some patterns that lies within some certain chunks. That's the difference between a simple recurrent neural network and an LSTM. Adam, you're going to have a class on this next Wednesday, or this Wednesday.
Yeah, this Wednesday.
So this Wednesday, Adam is going to have a class on how to actually build this. You're going to use NumPy. Okay, so using linear algebra, which is beautiful. And from that class, you will understand how you create these gates, how you're going to make the probability of forgetting actually you train that. It's going to be fun. But in a nutshell, that's it. And LSTM is a more complicated framework for remembering long-term relations and also short-term relations. Okay? More or less okay, yes, please.
So if we go back to Apple, so we say the central concept of LSTM is the memory, cell memory.
Yes.
To remember something. And so let's say Apple launched something last week, Monday, and stock price went up. So it's, went up. First day announcement, it just jumped 20%. Second day, investors like the announcement, it's still going up. But towards Thursday, it started to level off. Friday, this little movement. So you say, okay, I want to predict what the price is going to be on Monday, all right? So you have this information going back to Monday and even the week prior. You know Monday was a big event, so that's where the price. Mm-hmm. So you're saying LSTM, what it does is, on Friday, you already have the information, you have that context that something happened on Monday and it went up, but kind of level off on Friday. So what will LSTM give us on Monday? So it's saying, well, I saw the price going up, but I'm not really going to remember that because the last state I saw was that the price leveled off. So I will take that to consideration, the price going up, but I'm not going to put so much weight on that trend. But the last state was it leveled off. I'm going to put much weight on that. So, and then I'm going to combine that information because I'm going to keep that information for Tuesday's prediction. Is that what is it doing?
That's a very good explanation. And if you have enough past history on that, yes. So let's say that Apple already had 1,000 releases of some product. And usually the behavior, the release happened. Okay, let's use this as an example. Let's suppose that this here is the release of a product. It was released here. And so it was released here, okay, here. People got really excited. But actually this kind of overpriced. And people say, no, I'm going to realize this earnings. So it drops. But then again, people say, oh my God, but the product is actually good. Goes up and then goes down. And all of a sudden, here we're going to have a release. Again, and have a release, go up. If we have only this data, it would predict that it would go down. But remember that this happened almost 1 year before that. So it remembers 1 year before.
But it will forget it.
It's not only looking at the next the days before. So it remembers this kind of pattern, long-term patterns. It will remember patterns in the middle, depending on the size of the network that you're going to build. But it will grab a bunch of patterns. The most important one to diminish the loss function. If you have enough data, you're going to grab every single pattern. And when it repeats itself, he's going to say, look, this pattern here looks like this one, so probably this one. Now, there are some patterns here that we cannot see. That's why using an algorithm is so good. So that's the idea of using LSTM math. Yes. What remember becomes important. So you have here this cell here, the forgetting cell. It shows what you're going to remember, what you're going to forget in that situation. Remember, I'm going to do an analogy here, and I would like to use CNN to make the prediction on those on images here.
Yeah.
But like a technical analysis, I would love to do that, and I think it would work for this reason. Let me remember on image recognition. Let's say that I'm going to try to put in a nutshell. Let's say that this is an image. We have like, I don't know, okay, I'm going to try to draw something here. A person. Okay, now the computer, of course, it doesn't see a person, an image like this. It sees as a grid of variables, of numbers. So I'm going to pretend that it's just zeros and ones. I'm just going to draw the ones. So it would have a 1 here, a 1 here. One. Okay, pretend that this is this line. Okay. Now, remember that I told you that the weights on image recognition are actually like flashlights. They're like flashlights that you're going to go through convolving here, trying to get a pattern. And that this flashlight was a matrix also of zeros and ones that tries to get some pattern. Let me put here. So this flashlight is moving here. And it multiplies everything here, 0, so the result is 0. Now here, it's not going to grab, it tries to grab vertical lines. So it's going to grab this pattern here, this pattern here, this pattern here. This flashlight is going to grab only these 3 patterns. We are going to have a bunch of those flashlights convolving. And each flashlight is going to grab one pattern until the end you have an algorithm that is going to recognize these patterns, everything, because they have a series of flashlights. The same thing here. We're going to have the LSTM cells. We're going to have a bunch of those. And each one of those is going to be responsible to capture a given pattern. And those patterns is you're going to forget, you're going to remember, and the whole algorithm is going to be able to capture a bunch of patterns. The pattern might be a long-term pattern. It might be a short-term pattern. But you're going to be grabbing every pattern. That's the idea. It makes sense?
It might be a pattern, might be long-term, might be short.
It might be long-term, medium-term, short-term. If you have a good algorithm, a well-trained model, and of course, if the patterns exist, it might be just random information. Might be the case. If it is the case, there are no patterns. But if the patterns exist, it's going to grab.
You surely don't have short-term and long-term, right? It's either short-term.
No, you're going to do a short-term prediction.
Yeah.
You're going to do a short-term prediction. But the prediction that you're going to make, actually, you're going to see the pattern that is happening right now. And you're going to see, look, did this pattern happen last week? I have some cells that are going to capture that. No, that pattern didn't happen last week. And last month, there are other cells that grabs this kind of pattern, monthly patterns. No, and 2 months ago, there are cells who grabs patterns from each 2 months. Oh, it does. Also, I'm going to use those patterns to make the prediction. That's more or less the idea.
So is there some kind of internal mechanism where it makes a prediction based on one of the things in memory, and if it's close, it says, if it looks like this again, I'll weight that heavier in my prediction. But if I'm off by too much, then I'll try not to use that kind of flashlight vision to predict the next change. If there's as a learn, that's what it's doing, right? It's saying, I think this is a short term, I want to make a prediction, and then it sees how far it resolved, and it says, okay, maybe I should have picked a different type of prediction. And then that's how it learns.
That's perfect. That's perfect.
And then you move back to grab longer precision.
Now, you're going to have parts of the algorithm that are going to grab long-term prediction. Other parts are going to grab short-term prediction. Let's say that a given LSTM cell, remember that there's a forgetting gate, a selection gate. Remember from my drawing here? So if this gate, this particular cell was trained, the weights were trained to remember a given short-term pattern that happens, and it's happening something that is not short-term, this is going to enter the forget. It's going to pass by. The information is not going to be captured and moved forward. It's going to be captured by other things. This kind of algorithm grabs patterns. Remember, every single algorithm grabs patterns. If the pattern doesn't exist, there's nothing we can do. And usually, so that's the sad story here for those who thought that we would live here with a very good stock prediction model and everybody's going to make a lot of money. The answer is yes, actually. Look, not just kidding.
I got one.
All right.
I got an answer to that.
So that's the idea. But now we are going to and actually we have here. If you go down a little bit, probably we're going to have to run the whole thing. But let me show you how you build. Okay, building a model is actually very simple. Very simple. Since we are using this package called Keras. Basically, you are adding layers of LSTM cells. You have to put your input in a certain shape, and I'm going to show you on Wednesday how to do that perfectly, but actually it's fairly simple. And again, it's not, remember that, data science, it's not about the algorithm itself. Building an algorithm, building a model, is very, very simple. It's very simple. The problem is where you can embed an AI solution in your company, in your process, in whatever you are doing. And the largest problem, if you have the data for that. So everything starts with the data. You have the data. Yes, question.
So we're talking about short-term and long-term memories. Looking at this code, how do you manipulate it? If I said I want to have more long-term memories than short-term memories, or is there a way to go about that?
That's a very good.
Yes.
Yeah, there is a parameter on the set, like if we do the short-term prediction, I want to see the last week or last month or even last year pattern, is there any factor we can manipulate?
Yes, so let me ask if your question, if this answers your question. If you're trying to make a prediction of tomorrow, or if you're trying to make a prediction of next month, this we can do. But if you're trying to make the prediction for tomorrow and you want to emphasize the patterns that happens now or soon, I don't see why this would be efficient. Because it would be impossible to put that here. You can say that. I'm going to tell you why. If you're trying to, the goal here is to minimize the cost function. That's the backprop does that. You have a cost function. If you make a mistake, you're going to be penalized about this, and you have to update your weights. Now, if you're trying to predict tomorrow, and the pattern that is happening happened 1 month ago, and you're trying only to focus on patterns that happened in a short period, you're going to make a huge mistake. And the algorithm is going to try to correct that. So it's not going to work. Now, what you can do, if you want to predict, instead of tomorrow, you want to predict next week, now we are talking about how to set your X and your Y. Instead of doing just a shift of 1 day, you do a shift of 10 days. So you're going to have, instead of having, let's say that I have 15 time series, 15 points in time, right? 15 points in time. So I have here x1 until x40, and I'm trying to predict x50. I can set my database to do that, predicting 10 days later. So this will be x1 with x11, x2 with x12, and so on. If I want to predict tomorrow, it's x1, x2, x2, x3, x3, sorry, yes, that's correct. Does that make sense or not?
Can we do it with continuous wavelet transformation?
I'm sorry?
CWT, continuous wavelet transformation.
Sorry? Yes, please.
Short-term prediction. Is it possible to use a CWT to analyze?
I don't know CWT.
CWT is continuous wavelet transform, so that you
It
can
will
find the
give you
Mexican
the
hat
time
kind of
I can do, sorry?
like a Mexican hat kind of a waveform, and then try to predict based on for a short term. I mean, this question is long term and short term, right?
Yes.
So for short term prediction, it's quite difficult taking a statistical data of long term distresses. So
yes.
So if you take the short term CWT transforms and we gain what is called the short term coefficients, and then can we use the short term model as a repetitive model for next step prediction?
Look.
Yes. Within time domain, short term time domain, long term time domains, you have got various frequency components.
Mm-hmm.
And then if I have to predict tomorrow, I get certain coefficients. If I have to predict 1 week and ahead of 1 week, I get different coefficients.
Definitely.
So
So that's the idea here that I'm trying to say. Look, if I want to predict tomorrow, the database that I would input here would be like this. I would put first, let's say, I have to predict tomorrow. So tomorrow is 1 day after. I'm going to use the series that I have until a given day, let's say, until t minus 100, and this would be t minus, I'm trying to predict minus 19, 99, then this t minus 99, I'm trying to predict t minus 98. So that's how I build my x and my y. I will have an algorithm that will try to make this prediction. I'm going to train in here, just like we do regularly, always. If I want to predict next week, instead of t minus 99 here, I would put a week difference. So this would be 93, not 94, and 92, and so on. I just shift my y for 1 week. Then I build an algorithm that is going to predict what's going to happen in 1 week. I can build an algorithm that is going to try to predict what's going to happen in 1 month. But it's all about how to shift my y. The time that you're trying to predict, you shift your y. The x is the same.
So what you are saying is that you based on the trend that you learn from the prior data, predict the future trend.
Yes.
If the trend holds. If not, then your prediction will be.
Yes, yes. And now there comes the real question here, and that's there's another most important thing to have in mind. Let me see what time. Whoa. And a very important thing to have in mind. Domain knowledge is key. Algorithms are not going to substitute people who have domain knowledge. Because this question, the patterns that happens here, they are key. If we grab this example of Apple's example, we're going to see that the company changes throughout the time. The patterns changes throughout the time. Why it changed? Maybe the director of innovation changed. Maybe something else changed. Usually in financial market, the fundamentals of the company changed, or the fundamentals of the sector changed. Now, this is something that the specialists are going to import into the model. If you're trying to use this part here that has different fundamentals from this part here, you're not going to grab patterns. That's why when we did the stationary of the series, it had different patterns. So that's the key point here. And this happens for every single specialty. Being supply chain, being smart cities, in electrical companies, pharmaceutical companies. If what underlies the event changes, you cannot use the previous data. Nobody here uses the crisis data to make prediction of what's happening in space because the fundamentals changed. So there are some key ingredients here that are very important to understand, and that's why I like this class of AI, trying to put that into a business concept and not getting to the nitty-gritty of the algorithm itself, because we can have this kind of discussion. And actually, what matters? Where is the value? The value of AI. You have two places where you're going to have, as an individual, where should you invest your time to get knowledge? Should everyone here learn how to program? No. There are those who have to learn how to program. But most of us, we have to understand what's happening behind here, so we can understand where can we apply this kind of algorithms into our daily lives, into our solutions. And then you hire guys who knows how to code a lot. But you know what to demand. That's where the actual value lies. Yes, I'm going to bring some management jargon, which I don't know. But it lies on the protocols. It lies on the processes. That's where it is important. Questions? Yes.
Just mention, foreseeable stuff you mentioned.
Yes.
Yeah, so I've programmed over the last 5 years, I programmed ETF spiders.
Ah, so you're
Or 30, I'm up 30%.
Really?
And for the last 7 years, I was up at least 20. So, but that's on QQQ, that's a spider. But your integration is built in, so your short-term events, like Apple stock disappears. You know you're part of QQQ is IT products. But the integration is done with the sector.
Interesting.
Now, it's not right 100%, but I don't need it to be right 100%.
That's the point. That's the point.
And I'm making money at 30%. I'm real happy with that.
No, that's another point. It's not about the accuracy that you're going to get.
Right.
It's about the accuracy higher than the one that you used to get. That's the key ingredient here. when building an algorithm. What is a good accuracy? I don't know. A good accuracy is that the one that is better than the one that you had before. That's how you increase. Now, if you're making 30% a year, very good.
What do you mean by integration?
When you want to smooth, like
Yes.
this is what Apple does, is that you want to smooth that out. Because you don't know what every parent is caused by. There's too many variables. You can't predict it. Too many variables. Well, it's just, well, integration to smooth it. That still doesn't give you enough to train it out.
The eye of Arima is the diff part. The differentiation, the diff part is.
No, I understand.
Okay, guys, thank you very much. If you have questions, we can talk further. Wednesday, we have the fundamentals of AI with LSTM. Saturday, we're going to start the project on something related to finance. And let's do something related to supply chain as well. Those are the ones. Thank you very much.